All right, guys, so here's number 98. One of the reasons I wanted to do 98 is just to remind you of how to work a complex fraction. First thing I'm going to do is prove that it's actually an indeterminate form. So if I plug 0 in for h here, using direct substitution, I'm going to have 1 over a plus 0, which is 1 over a, minus 1 over a over 0. I already don't like the 0 on the bottom. That's bad. So now that's going to end up giving me a 0 over 0. That is an indeterminate form, and like I said, that's bad. I don't want that. Now, we can all agree that that's bad. I'm going to erase this because I'm going to need the space. We are going to do a little bit more algebra than we did in the previous ones. This is a pretty cool problem. So this goes to that complex fraction that blocks about problem solving strategy talks about. I think it's part C on number 2 there. So they say we're going to start by simplifying it. There are a couple ways to simplify complex fractions. If you recall, one way to simplify complex fractions is to work the top, work the bottom. So you get a common denominator for the top, work it all the way down. Common denominator for the bottom, work it all the way out, and then you clean up that last division step. I think that's actually harder, more time consuming. So I'm going to talk about the other way to do this. The other way to do this is to find an LCD of everything, and that's what I'm going to do. So I've got 1 over a plus h, so I've got a denominator that's a plus h. I've got a denominator that's an a, and please notice you've got the h on the bottom of the fraction. That h is actually over a 1. So on the denominator, I've got a 1. So my LCD for everything, and I'm going to do this in a different color so we can kind of keep track of what we're doing here. Let's do it bright blue. So my LCD of everything is all the different common denominators that you found. So a plus h is one of the denominators, a is one of the denominators, and 1 is one of the denominators. And so my LCD is going to be 1a times a plus h. Now, of course, I'm not going to take the 1. It doesn't do anything. So I'm just going to write my LCD as a times a plus h. And once I find that common denominator, I'm going to multiply every single thing by that common denominator. And if you have done this process correctly, you should see denominators canceling out. So I'm going to multiply this fraction by a times a plus h. I'm going to multiply, these boxes. Go away, box. Can you disappear so I can write? Okay, we'll just pull it down here. Me and Zoom we're not getting along right now. I'm going to multiply this fraction times a plus h. And then I'm going to multiply this bottom part by a times a plus h. So everything, every single fraction in here is going to get the a plus h. All right, put this box back up here. So what's that going to leave me with here? No, I can't either. If you will notice in this first fraction, you see how it's got an a plus h in the denominator and a plus h now that I'm multiplying by? Those two are going to cancel out. Here I have an a and an a. Those two are going to cancel out. And then on the denominator of this complex fraction, I have an h. Remember that h was over 1. Nothing's going to cancel out here, and that's okay. So let's talk about what we have left over now. So I've still got the limit as h approaches 0 because I've not taken the limit yet. I've got 1 times a. So 1 times a is a minus 1 times a plus h. So I'm really distributing up my negative. So negative 1 times a plus h is going to give me negative a minus h. And then on the bottom, I've got h times a plus h. I'm not actually going to distribute it out. You're going to see why here in just a moment. So now we have the a's canceling out. They're gone. So on the numerator here, I have the limit as h approaches 0 of negative h over h times a plus h. One of the reasons I didn't multiply this out is, do you notice how we've got an h on top and an h on bottom? Guess what that's going to do? Well, that's going to cancel out. Guys, remember when you're canceling out stuff, you're technically getting 1s in its place. So really, there should have been a 1 up here. This would have been a 1 down here, so on and so forth. It doesn't really make a difference in the denominator. Where it does make a difference, though, is in the numerator. This stuff that's in the denominator, it doesn't automatically just flip back up and become in the numerator now. You have to have that 1. So now we have the limit as h approaches 0 of -1 over a times a plus h. I do believe I am ready to do my direct substitution. I think this is going to work out really pretty. So we're going to have -1 over a times a plus 0. And when we do that, we do end up with the statement -1 over, well, a times a is a squared. The 0 doesn't do anything. So we do end up with it being -1 over a squared. This is different than what we have seen up to this point. At this point, or up to this point, we've been seeing numerical answers. And now we do have variables in the answer. And that's okay. That's fine. You can get answers that have numbers or have variables in them. All right, cool. So that was a complex fraction. So now at this point, we've seen an example of what to do with the factoring side of it. We've seen an example of how to get rid of radicals, and now we've seen an example of how to get rid of complex fractions. I wanted to make sure that I had an example for you to look at. I'm going to do one more of these particular problems, and that's going to be number 99. With number 99, it is a trig equation. So I want to make sure we've seen at least one of those, because I think by the end we've hit all of our things. So we've got limit as theta approaches pi. How cool. So we've got sine of theta over cosine of theta. Man, my thetas are really hard to draw on this screen. Now, if I was to do direct substitution from this step, I would end up with, well, the sine of pi, of course, is 0. And it actually turns out the cosine of pi is also 0. So we do end up with that indeterminate form. So I'm going to try to clean this up, guys. Now, Trig's going to function a little bit differently than everything else that we've done. So I'm going to try to reduce this using trig rules. Oops. No, I wrote this wrong. Sorry, guys. Sorry, that is my bad. This was not a cosine. Oh, man. This was not a cosine. This was supposed to be tangent. I looked at 2 different problems because I'm thinking the cosine of 0 or cosine of pi is not 0. There we go. This is a tangent. I apologize for that. That is a tangent of theta. Okay, so now we've got sine of theta over tangent of theta, so we do have the indeterminate form of 0 over 0. I was wondering why we got 0 over 0. Okay, see, if we were actually had a class, you'd be yelling at me right now, like, what are you doing? That doesn't make sense. So to clean this one up, I'm really going to focus on this idea of tangent of theta, because tangent of theta is composed of a couple of different things, right? Tangent of theta is actually composed of a sine and a cosine. So there is a way to rewrite tangent of theta in terms of sine and cosine. And if you remember anything from trig, we almost always want to try to put things in terms of sine and cosine. So I'm going to keep my sine theta the same, but I'm going to rewrite tangent of theta to be sine theta over cosine of theta. Now, it doesn't look like I've done a whole lot because it still looks like an indeterminate form, right? I'd still have 0 over 0, which is not helpful. But watch what happens here. I know that I've got sine of theta divided by this big mess down here on the bottom. And I know that when you're dividing by a fraction, division by a fraction is actually equivalent to multiplication by the reciprocal. So I'm going to multiply this sine of theta by the reciprocal of sine theta cosine theta, which is cosine theta over sine theta. And look what happens now. The things that go to 0 cancel out. The sine theta is gone. So now I have the limit as theta approaches pi of the cosine of theta, which actually turns out to not be 0. The cosine of pi, because I can do my direct substitution now, is -1. Cool. All right, so there's those particular problems. Guys, I do want to do I do want to do a couple of other problems here. We're going to kind of switch gears though. I think we're going to look at one-sided limits now. So we'll talk about some one-sided limits. See you in the next video. All right, guys, welcome back. In this video, I'm going to do problem number 103 and 105, which are the two examples that they have or that I have picked out to do one-sided limits, because it's been since the previous section since we talked about one-sided limits. I do want to remind you that in the previous section, we talked about infinite limits. So we did talk about what happens when you have infinite limits. And a lot of times when we had one-sided limits, one of the reasons we did one-sided limits is because the actual limit didn't exist, but we could find a limit from one side or the other. So whether it be the right side or the left side. Now, with that in mind, there come special rules with that. So there was a box on page 146 that talked about infinite limits. And then there was another box on page, it was actually theorem 2.3, since you probably can't see the page numbers, but in theorem 2.3, it did go over the types of infinite limits that we saw. So sometimes, you know, coming from one side, it would shoot off to positive infinity, or it would shoot down to negative infinity. So we're going to keep that in mind as we go through and do these next couple of problems, because they're really strange. So I'm going to look at number 103. So let me make sure to share my screen with you, or you're just going to see me talking instead of looking at stuff. So number 103, they do tell us in the following exercises, use direct substitution to obtain an undefined expression. So we know we're going to get something undefined. Then use the method of example 2.23 to simplify the function to help determine the limit. All right. So 103, we've got the limit as x approaches -2. Now notice you've got the negative on the right side there. That means that we're coming from the left, right? So when the negative is behind the 2, that means from the left. If it was a little plus sign behind it, it would be coming from the right. Of 2x squared plus 7x minus 4 over x squared plus x minus 2. All right. So let me pull up a whiteboard so we can look at it. Find all of these stupid boxes. So 103, we had the limit as x approaches -2 from the left of 2x squared plus 7x minus 4 over x squared plus x minus 2. Okay, so if we were to do direct substitution, I would plug in -2 into all of my x's here. And guys, I'm going to assume that you're okay with the math. If I plug in -2 on the top, I do end up with -14. If I plug in -2 on the bottom, I do end up with 0. That is an issue. That's undefined. So I've got to somehow try to fix this up. So let's go back and see what we can do with this. So we've got the limit as x approaches -2 from the left of 2x squared plus 7x minus 4 over x squared plus x minus 2. We kind of looked at something very similar to this in the previous, not the previous video, the video before that. I've got a polynomial here, and I'm pretty sure this polynomial is going to be factorable. So I'm going to go through and I'm going to factor the top and the bottom. So if I factor the top out, and guys, again, if your factoring skills are not good, you need to practice that. Factoring is something that you just cannot do without in this class. So if I factor the top, that's going to give me 2x minus 1 over, or times x plus 4. So that's what the top factors out. On the bottom, I'm going to end up with x plus 2x minus 1. And unfortunately, even though I did factor everything out, nothing cleaned up. So now what? Well, let's talk about what happens. if I was to plug -2 in here, I would see, now we know the top's going to be fine, right? The top worked out fine before I factored. What I'm trying to do here is I'm trying to figure out what piece of the denominator here is sending this thing to 0. So where am I going to get the 0? And I do think the 0 is coming from this piece right here, right? If I plug -2 in, that's going to make that go to 0. However, if I plug -2 into the x minus 1, I end up with -3. So that part's fine. It's the x plus 2 that's not fine. So what I'm going to do is I'm going to pull out that x plus 2. So I'm going to write this a little weird. So just bear with me. There is a reason we're doing this. So we've got the limit as x approaches -2 from the left of, now I'm keeping everything the same except for x plus 4. And I'm having to write small because I'm running out of room here. That's left there. X minus 1. So all that's fine. And then I'm pulling out the 1 over x plus 2. So I pulled out the piece that's going to make it go to infinite, or excuse me, to 0. Now I'm going to actually go back here in just a second. So let's do a direct substitution right quick. So if I plug in -2 right now into, like this piece right here. So if I plug in -2 into that piece there, let's talk about what we get. So the limit as x approaches -2 from the left is going to give me 2 times -2, which is -4. -4 minus 1 is -5. If I plug in -2 for x plus 4, I'm going to get -2 plus 4, which is 2. And then -2 minus 1 is going to be -3. So with this piece, I'm going to get a numerical value. It's the 1 over x plus 2 that is not going to give me a numerical value, or at least not a pretty numerical value. So what I actually want to do here is I'm going to go back, and hopefully you're going to be able to see my screen. I want to go back and I want to look at some of these theorems here. And I think to do that, I actually, let's see, can I pull up the book? Would that let me do it? Look at that. Look at me being smart. So I'm looking for theorem. What did I say? I tell you guys this stuff and then I go and forget it myself. So I want to find theorem. (2.3). So theorem 2.3 is what I'm looking for. Ooh, here's all of our this is our 3 different types of infinite limits. So we talked about that in a previous video. Still looking for theorem 2.3 though. Ah, here we go. So please notice infinite limits from the positive integers. Now guys, let me make a note here. I'm going to write on this and I'm going to say, I'm scared that you can't see my screen. I'm scared. I want to make sure you can see my screen. Okay, so here, looking at this is theorem 2.3. I want to look at that piece of 1 over x plus 2. That's the piece that I'm kind of interested in, because I think it's going to do one of these things. So let me write that piece out, 1 over x plus 2. Now, remember, this was going to be the limit as x approaches -2 from the left. So I'm trying to figure out which one of these rules relates to that. So here, this particular rule here is if you're coming from both sides. That's not what we're doing. We're coming from the left. So that's got to be this rule right here, right? And this says that, if you've got the limit as x approaches a from the left of 1 over, now this does say x minus a raised to the n. I can factor out a -1 and make it look like that. We don't have to go through that process, but it's going to end up being negative infinity. So now with that in mind, I know that one piece is going to go to negative infinity. So let's go back and look at our whiteboard. So I believe I've got to clear this out. Okay, so let's go back and look at my whiteboard. Where's my whiteboard? Come on. Don't let me down. So now we've got this statement, that 1 over x plus 2, when I took the limit of it, ended up being negative infinity. So now I've got this statement. I've got -5, no, excuse me. negative 10 over negative 3, which is actually a positive 10/3, right? So I've got a positive times a negative. So yeah, 10/3, woohoo, whatever. 10/3 doesn't really do anything to infinity. What I'm more concerned with is what's the sign going to do to infinity. So I've got a positive times the negative. This is still going to stay a negative infinity. So this one-sided limit, so when I'm approaching from the left side of this particular function, I am going to see it as I get closer to negative 2, it's going to head down towards negative infinity. Guys, remember, if you don't believe me, you can go through and you can look at it graphically, and it's going to show the same thing. But this is how we proved it algebraically. Again, it's a little weird because we had to take that one piece out that wasn't working for us, and then I had to compare that to theorem 2.3 where I found it was negative infinity. And once you start pulling out infinities and trying to work with them algebraically, it can get a little confusing. Infinities are actually really hard to think about, but what you're trying to do here is you're just trying to find the signs. So you're trying to see if the signs are going to be adjusted at all. So that was number 103. I want to do one more of these so we can look at it. Maybe. Does this one do anything different? This one doesn't do anything different. So you know what, guys? There's really no point for me to do it again because it's the same exact thing. It's actually the same exact function. It's just like they look at it, the approach is one. Okay, so cool. So I'm not even going to bother with this one. It's the same thing, same problem. So we're going to leave it be at this, but that's how you look at a one-sided limit. And typically with this particular book, when they do these one-sided limits, they're looking at an infinity with these particular problems. All right, so I'll come back and we'll look at something a little bit different in the next video.